Hey guys, today we are going to talk about dielectric series and dielectric convolution. First, dielectric convolution. Okay, that's a new term and it's something, an operator between two functions. Functions like f. Let's one function be f and another function be g, and a new function h is defined to be the dielectric product of f and g. This is a new notation to you, right? This is called dielectric convolution. But first, what is dielectric convolution? But before that, we need to talk about these two functions. F and g can be arithmetic functions. And let's talk about range and domain. F and g maps the natural numbers to complex plane. Okay, that's rather interesting. But how do you define? So this is equals to sigma, as it's usually written, d of n. I will explain this. And f of d times g of the n by d. Okay, what this says basically, d this right here, this right here means that d is the divisor of n. So if you take like a number 10, if n equal to 10, then you would get d is 1, 2, 5 and 10. Okay, and the this can be written as a more, you know, simpler way, a times b equal to n. So we are talking about pairs of numbers which satisfy this condition, and f of a times f of b, g of b. This is the definition of a dielectric product. Interesting, right? Hmm. Well, okay, that's interesting. So you might ask, can we do an example? Okay, we will do an example. Uh, now you know, uh, let this be in a box. Another an interesting and most important formula in number theory and analytical continuation. We'll see why this, rather absurd definition is useful in continuing the dielectric product. And yeah, you'll just see how it works. Now let f be x square, of course, x square. Actually, written like n square is better because we are going to deal with natural numbers, and g is going to be, well, for simplicity's sake, n. Okay, how do you define the product? So f convoluted by g is actually a function of n, and this function is going to be equal to sigma a b is n and f of a times f g of b, and take pair. Now let n equal to 10. And let n equal to 10, and just put it in, and a can be 1, 2, 5 and 10. Okay, so we will just do, so this is f of 1, so the corresponding b would be f of 10, g of 10, and so on for the rest of the terms. As you may notice here, it's very evident that this is very interesting because this term, if you just reverse this product, you can find that F convoluted by G is actually G convoluted by F, another rather interesting property. Well, now we will just compute this. Now you will take 1 square times 10 plus 2 square times 5 plus 5 square times 2 plus 10 square times 1, and this is equal to 10 plus 20 plus 5 square into 2 is 50, and then you have 10 square into 1, which is 100. This is 180. Okay. Okay, so that's just convolution. And now we are going to discuss the properties of convolution. We will see why this matters in a moment, but bear with me. F convoluted by G is equal to G convoluted by F. This is rather an interesting property, and this can be extended. F convoluted by G, the whole convoluted by H, is going to be equal to, F convoluted by G convoluted by H. A rather an interesting property. But I haven't told you why convolution is essential yet. Okay, for that you need to understand the need of a dielectric series. Now, a series is something like a sum. We are now talking about an infinite sum, and starting from n equals 1 of a function, any function, by n to the s. S is some number. You could define a function like this. It's particularly useful in the Riemann hypothesis. Okay, now you want the product of two distinct dielectric series. Then this would be, to everybody's shock, sigma, another dielectric series. Oh, and do you know the function? Convolution of those functions. Okay, that's basically dielectric series for you. And I'm going to briefly talk like f of n. If f of n is a function, then we have such a function called identity function that returns, the same thing. Just like product of one number is times 1 is 1, you have convolution by this identity element is 1. The identity element is 1 for n equal to 1, 0 for other n. Okay, that's it actually, and that's it. So we are going to conclude our video by saying that the dielectric convolution and dielectric products are very useful in continuing analytically some functions. Well, you will see more about this maybe in a later video, but that's the topic for another Feynman video.